So we're just getting started on our geologic time unit, and you did a couple practice problems or scenarios with your activity previously, thinking about pizza and laundry and lockers. And we're going to start applying those ideas today as we think about some real cross sections, keeping in mind our unit question of what evidence can we use to determine the geologic history of the Earth. So what can we see today to figure out what the Earth looked like before? So you should have already read through this quick summary, giving some background on what geologic time is, absolute time and relative time, and how they can be applied to give clues about how the Earth got to be the way that it is. So you've got a couple questions that you already answered right here, and we're picking up right here then, relative time rules. So here we go. So like we said, this idea of geologic time is taking what we know and what we observe around us and putting things in order. So something like this would be really simple because we have context with it. We've experienced at least one of these three things. But when we look at a picture like this, it gets a little bit more complicated, and we don't have those contextual clues just to use. So we have to make sure we know and understand what those rules are for ordering a picture of a cross section like this, or maybe a picture of a cross-section like this. And so when I'm using that word cross-section, what I'm referring to is this whole picture. So cross-section is thinking about a piece of the Earth cut so we can see it from the side. And really, you could have a cross-section of anything. You could have a cross-section of an apple or a car or a tree, just to get the idea of what's going on inside in an area that we can't necessarily see. So again, you talk through relative and absolute time. You've got your answers going here. We're starting to think about then these rules. So to get those contextual clues like we have with the cake or the beach or the pile of laundry, we need to know a little bit about how rocks come to be. So one of the main rules that we're going to use all the time is this one, principle of original horizontality. And in that big phrase, I know this sticks out to you, horizontal. We know what that means. That means, flat, like this, horizontal. And then we have the word here, original, thinking about first or initial, something like that, where it began horizontal. And that's really what this rule is getting us to think about. So on your assignment there, you can be filling in what this rule means. Well, it means that layers of rocks have to be deposited horizontally when they start. Okay, we can see all kinds of really cool and crazy looking rock formations, but we know they didn't really start that way. They had to begin in this horizontal state. So not only do we want to have our definition recorded, but we're going to draw a little picture for each one of these to help lock in really what it means. So this particular one, we're actually going to split the square or rectangle in half, and we're going to kind of do like a before and after. So this is the original side, like how everything started. And then this is the after or the later side, maybe what we would see today. So again, our rule of horizontality says that, well, rock layers have to start horizontal. So we're just going to do a quick 1, 2, 3 lines to give ourselves a couple layers. And from what we practiced yesterday, we can start thinking about where the oldest and the youngest are once we get through this idea of everything had to really start or was originally horizontal. So this is how layers maybe have to begin. I'm actually going to do one more in here, I think. And then the after, well, now we can see those same rock layers not horizontal, right? We can find them all over the place on Earth looking differently. tilted or folded or faulted, and we'll start to see what those things really look like. So original horizontality means rock layers have to start flat or horizontal, and then they can be changed afterwards. They aren't going to start looking like this. And so for each one of these rules, we'll have our official definition, we'll have a picture, and then we also are going to give a little nickname. So this one is known as the rule of cake layers. So add this into your lines, maybe highlight it or keep it a different color like I have. So rule of cake layers is, do you ever watch those shows that are like Cake Boss or whatever, where they make a really fancy cake, like a fire truck or a unicorn or something? Well, thinking about that cake, it had to start like this. It had to start as flat cake pan layers. After it comes out of the oven and it's put all together, it might look like that fire truck or that unicorn, but originally it had to start horizontal. So that's our reminder, our cake layer rule. Our next one here, the law of superposition. Again, if we break the name down a little bit, we know position or like location of the rock gives us a clue about them. And the clue here has to do with their age. And a lot of you were on track thinking through this yesterday, like with the locker or the pizza, thinking about where I can find the oldest or the youngest parts of a cross section, like we said, that side view. So the superposition rule, or the law of superposition, reminds us that we look towards the bottom of a cross section for those oldest layers. They had to be there first. They had to get placed initially before other younger layers could then be piled up on top, if you will. So our youngest layers are found more towards the top, while our older layers are found more towards the bottom. And again, we're going to draw a picture to represent that law. So in the box that you have there on your notes, we're just going to do another simple 1, 2, 3, and then we'll make this one, kind of wavy. So this is like our surface. All right, there's a house, a little tree. So when we think about ordering these, again, oldest on the bottom, well, our oldest layers get the number of 1. They had to happen first. And then 2, 3, and 4, right? This up here doesn't get a number because that is the sky. So again, our rule is telling me the oldest or the first layers happen at the bottom, and my younger, more recent layers are happening at the top. So again, thinking about the nickname, I like to call this one the dirty laundry rule because again, like that activity, we know the older clothes are down at the bottom of the laundry pile. So like the Monday, Tuesday are found at the bottom, where the Thursday, Friday, Saturday are more towards the top. So the younger rocks, just like the most recent clothes, are found at the top. And so that would maybe look something like this in real life. I don't know if this looks familiar at all, but this is the Badlands. And you can kind of see here the different layers that exist within this beautiful outcrop. All these rocks are naturally layered and perfectly flat. And these type of rocks are typically a sedimentary rock. And I know you've heard this word before, so just a quick reminder. But these sedimentary rocks are formed from pieces of other rocks. So you could be highlighting a couple things as we're reading this section here. But they're tiny pieces of rock. They're called sediments, hence the name sedimentary rocks. And they get, as you can see in this picture, deposited, compacted, and then cemented together, usually in some sort of water environment. So an ocean, a river, a beach, delta, coral reef. So we see those rock layers form at the bottom of those waterways, and hundreds of thousands, millions of years later, they solidify into these rocks that really, again, can be found on the Earth's surface here today. So this at one time was the bottom of some sort of water environment, and now it's on the surface for us to enjoy and admire today. And you can see in this little animation, these layers are starting to form here with different characteristics, right? Different grain size, different materials, and therefore different rock types. So when we start to see these forming in our cross sections, we might have a layer of like this conglomerate, then a layer of sandstone, maybe a limestone mixed in here. And so we'll start to see those beautiful horizontal layers forming. So typically when you look at our cross sections, those horizontal layers are almost always a sedimentary rock. That's always a good place to start. They don't last horizontal forever though. Like our horizontality rule reminds us, is they start horizontal but can get deformed later. So again, this is a real rock cross section. This is a real outcrop. And again, this one too. They didn't start this way, but they began horizontal and then something came through and changed them. And that's what you're looking at here, different ways that rocks can be deformed. So this first one here looks kind of like waves. We actually see, similar to this picture, we see rocks starting to become wavy in real life, and that has to do with tectonics, right? The earth is being compressed from two sides, and over long amounts of time with continued pressure, those layers can form these waves, and we call those folds. So go ahead and fill this box in with that word, folding. And so when we start to not only recognize what happened, but also put layers in order, what we would do here in the middle is we would say what layers are in fact folded. So there's nothing for us to fill in right there, but say on a picture like this, we would know that all three of these layers are folded. So we would say, layers 1 through 3, but this is kind of like our outline to use later. So you don't have to fill anything here right now, but just wanted to mention it as we kind of start moving forward. We'll start to see that same patterning pop up. Another thing that can happen to rocks is this. You maybe recognize that this area here looks the same as this area here, and it is. It was at one point one big flat sedimentary rock layer, horizontal, but now it has this huge crack running through it. And when we think about those cracks, that offset layers, bump one up and one down, those are known as faults. So in our cross sections, we're going to start to look for some of these deformations, and we're looking for these actual cracks where we have rock layers that we can see have slid from their original state of being horizontal. And again, that's from tectonic pressure. And that can really happen from either pushing or pulling, but these cracks occur and we see one piece rise up while the other piece really sinks down, and again makes those layers offset. So again, if we were doing this on a cross section, we would have track of all these layers and we'd be able to say, okay, layers 3 through 6 got faulted or whatever it is. But again, nothing specifically to fill in right now. The last deformation, well actually not the last, the next deformation we're going to look at is this one. And again, we can see these super nice, pretty consistent layers, like they're one right after another. And there's not a whole lot of change to them, right? They're just, hopefully you can recognize, tilted. They're tilted here. Here's another example. These are much bigger. Okay, this is somewhere on my bucket list. This is in Colorado. It's called Red Rocks, and as you can see, it's like a concert venue, and there's another one of these on the other side of this amphitheater, kind of acting as the natural walls for acoustics. Looks pretty cool. So anyways, these rocks are tilted. So they started, again, horizontal, but different things shifting in the earth have caused them to now appear sideways or tilted up a little bit. So different movement of tectonic plates can create this tilting. And so again, this is what it would look like. These layers have been tilted to the side, and they can really go either direction. And that's what we would recognize. So we have folding, we have faulting, we have tilting, all things that would change a whole area that was originally horizontal, and then movement of the earth has deformed it or changed it. Now this one here, we do definitely still see the horizontalness, I guess, of this rock, but what's tricky is this here is not a sedimentary rock. It actually is something that pushed through this existing layer, and maybe you can tell kind of burned it a little bit. So thinking along those lines of burning, maybe you're remembering a type of rock that comes from molten material, and that is, of course, our igneous rock. And we think a lot about igneous rock with this idea of cross-cutting relations. So this rule has to do with, again, layers that exist but have been cut through. So we're actually going to draw our picture first here. So we're going to start with just a few basic layers, that 1, 2, 3, 4 again, okay, without numbering though. So we have those 4 existing layers, and then we want to draw that igneous rock cutting through. So I'm going to draw in something like this. So you can be drawing this into your box as well. And this is like that rock layer we just saw in the picture. Something that cut its way through some sedimentary layers. Again, our clue that these are sedimentary is that they're so horizontal. Our clue that this is not sedimentary is it's going through something else, almost in a vertical fashion. So when we think about this rule, what we know is that any igneous rocks that we see cutting through, or any faults, because they cut as well, it's kind of our key connection here, cutting, they have to be younger than anything they cut into, meaning they have to come after those layers that they intersect. So there's not a way that this layer could be first, because if it was first, well, there'd be nothing for it to cut into. So with that analogy you used yesterday, a good thing to kind of think about is that pizza cutting, right? Everybody knew to cut the pizza was last. Just like here, any igneous rocks or faults have to be last for layers that they cut. So I can't necessarily say that this is after these because it's not impacting it, but it sure is have to come after those. I also like to call this rule sometimes the rule of the photobomb, right? We know photobombs are when you kind of jump in someone's picture that's already going on. So again, these guys have to exist, right, before this can photobomb. These have to be the original before you can cut into it, whether that's like the pizza cut or the photobomb cut. So when we go to number these, we're looking at the bottom for the oldest, just like our superposition rule. And we'd have to think about, well, this has to exist first in order for that igneous rock to cut through, as does this one. So that has to be 1, 2. Then this came in, cut through those, followed by the remaining layers on top. Because again, that igneous rock doesn't cut or intersect those. So again, this happens a lot with igneous rocks. So just a reminder, those are rocks formed from molten rock, either magma inside the earth or lava on the outside. They start somewhere down here on the interior and push their way through, again, these rocks that already exist. So these surrounding rocks had to be there first before any of this igneous could push its way through. And you'll start to see a couple maybe new terms with our igneous rocks. An extrusive igneous rock formed on the Earth's surface, so anything forming up here in the atmosphere, that's an extrusive rock, whereas anything forming inside the Earth, like as this cools or this starts to cool, those would be our intrusive igneous rocks. And again, these igneous rocks typically, there can be some, but typically do not appear horizontal in our cross-section. They're usually cutting their way through these other rocks. All right, our last big idea to think about then is this one, unconformities. It's kind of a weird, fancy word for a really simple idea. What an unconformity is a spot where rocks have really gone missing. So what we're recognizing is that because something went missing, what we're thinking about is a piece of the Earth's history that we know nothing about. It's really a gap in time or a gap in that rock record. And we can see on this picture here how these two areas look so different, right? The top looks extremely different from the bottom. It's not that we would have a huge shift like that. It typically tells me that, again, something has gone missing. And so things that cause rocks to go missing or be taken away has to do with weathering and erosion. And we'll give a few examples of that here in a second, but that can only happen on the Earth's surface. And so this contact line, as we called it, often shows up on our cross sections as like dark wavy lines, giving us a clue that some sort of erosion happened while that rock layer was on the surface, and something got removed, went missing, and then new layers got deposited on top. And then we just don't account for that gap, right? This would be like 1, this event would be 2, and then new layers appearing as 3. We don't know how much went missing. 1 day, 1 year, 100 years, 1,000,000 years, we don't know. But what we do know is that there was just a shift in what was going on, and so something is missing. So in our cross sections, they're going to look a lot like this. And you have these 3 pictures on your notes page there. And hopefully you're recognizing these wavy lines, right? This would be an unconformity. Okay, and hopefully you can highlight that in your notability so maybe you can see that darkness of the line through and recognize how, flat and horizontal these are. Okay, even here, you can tell that these are not wavy. They're original rock contact lines. This rock came and this one and the next and next with real no interruption. But that dark wavy line, if you highlight that on all 3 pictures, that is your unconformity, and maybe label them up. So in our cross sections, our side views of these rocks, that's what we're looking for, is these unconformities where we know there was some sort of change in what was being deposited. So again, here's our last one. So like we said, these are coming from weathering and erosion. So what does that even mean? Well, like we said, just as easily as rocks can be deposited, they can actually be taken away. And there's a really great visual of how rocks started full or complete, right? We've got a layer here of shale, sandstone, or shale, limestone, and sandstone, and then something's coming in and removing them. So maybe you can recognize that dark wavy line that would appear in our current view. And so things that cause these unconformities, weathering, erosion, you're seeing examples right in here. Any kind of water, so we're thinking about like rain or rivers or waves. Water is a huge weathering and erosion factor, creating unconformities. Another one can be wind. Now that obviously can't move as big of pieces of sediment as water can, but it can still move sediment either way. And our final one here is ice. And that can really happen 2 ways, either like glaciers can carve out the earth, or even here in Minnesota, we have ice weathering and erosion, or weathering and eroding like our roads. So that water can get into a little crack over the daytime, and then as it freezes at night, it expands and starts to kind of wedge that apart. So water, wind, and ice are all ways that these unconformities can happen. And rock can, like we said, go missing. So the last thing we're thinking about here is kind of like what we did with those deformations is, well, what would that look like when we're telling that story of geologic time? So we know weathering and erosion would create that. We would have to say what layers are affected, like here it'd be layers 2 and 3 because no erosion that we can see to this original layer. And then that creates the unconformity, the gap in the rock record. And sometimes we might even be saying, well, it's creating that uneven surface. So if this scenario just ended, this became the surface of the earth, well, that's what would be being created, that uneven surface spot. So again, this is something we're going to keep coming back to. Just wanted to point it out as we got started. And we're just looking here at an actual unconformity. So maybe you can see some of those horizontal layers here, but there is this one wavy spot where we know this layer got deposited. Something, we don't know what exactly from our initial look, but we can investigate and look for more evidence, more clues, and see, well, what maybe would have taken part of this layer away and then added these new layers here on top. So pretty cool. So at this point, you've, again, read your first page, answered a few initial questions, worked your way through both definitions and pictures for our couple rules, thought about ways rock layers can be deformed from their original state, and you are right here, ready to fire up that cross-section 1 next time we're together.